Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's take a look at today's Bellwork exercises. Today's Bellwork, right, you'll be allowed to use these, the graphing calculators and their built-in functionality in order to solve a system graphically where we have a non-linear component at this stage, as well as a 3x3 system. So let's take a look at each of these. And for the first one, we can go ahead and enter each of my y equals equations in my y equals menu, graph them on the same xy coordinate plane, and then use the built-in capabilities of the calculate menu, right? Second, calculate intersect. So let's go ahead and check that together. For number one, I'm going to go ahead into my y equals menu and clear out my previous functions. I can zoom 6 to return to a standard -10 to 10 viewing window. Before entering my functions, I'll call that first one y1. So that was 2x squared minus 3x, and if you guys would make sure I don't make a mistake, 2x squared minus 3x plus 1, and then my second function was -2/3 x plus 8. So we'll go ahead and grab that. And now I'm going to go ahead and see what my standard default window looks like. If I can see intersections, I know I'll be able to find those solutions, right, based on my picture. If I can't, then I'll manually adjust the window. Here comes my first one in the blue line style. That's a parabola, as we'd expect, because it was a 2x squared equation. And here comes the second one in the red line style, and it looks to me like this line intersects that parabola not once but twice, and this makes sense. Are there any other points of intersection hiding out there? Well, no, because we know the behavior of a parabola changes direction only one time, and our line is a constant rate of change, and so if I can see both intersection points, I know there's no others hiding out there. And so what I'll probably do is make my window a little bit different, so it'll be easier for me to find that. In fact, I'll shrink my x window maybe -5 to 5, and I'll make my y window taller and not quite as low. So I'm going to quick do a manual change here. I'm going to make my x window -5 to 5, so I can get a better picture. I'm doing this through inspection, right? There's no right or wrong window necessarily. I'm just trying to get a better picture so it's easier for me to calculate the intersection points. It looks like I could go -2 to 15. And now I think it's going to be easy to do my second calculate intersect. There's my blue parabola. Here comes my red line. And that's a nice window. So we'll go ahead and find those intersection points by doing second calculate intersect. So here we go. Second trace is the calculate menu. We want the fifth option, that's intersect. First curve, enter. Second curve, enter. And then for my guess, I need to use the left or right arrow keys to get closer to one of the intersection points. It'll automatically jump to the closest point of intersection. So first I'll go ahead and find the left one. As long as I'm closer to the left one before I do my guess, it'll jump on the left one, and it looks like it returns the xy ordered pair. So it looks like x equals -1.376 and y equals 0.9175. And then I could go ahead and find that other intersection point by doing second calculate intersect. The fifth option, first curve enter, second curve enter. But now I need to get closer to the other intersection point. Otherwise, I'll just keep returning that first one. So I've got to go closer to the other one. And when I do, I can press my guess. Voila! And the calculator will jump onto that second intersection point. And so remember, we still want to make sure that we're answering the question that was asked. And here we wanted to be equitable. So we're still going to write our solution points as coordinates, x comma y, because we're solving a system. So we want both of these, and we're going to go ahead and write those as ordered pairs. So it looks like -1.376, the three places past the decimal point, is paired with 8.918. Is that what you guys are getting? 8.918. Raise your hand if you had found this left solution point in green. You found the left solution point in green? Good job, you guys. And the right one, I'll go ahead and do in blue, and that was about 2.543, comma, 6.305. And raise your hand if you're on the blue intersection point. Who found that blue intersection point? Way to go, you guys. That's awesome. What questions do you have about second calculate intersect? So then, on your quiz, if you're asked to solve a system graphically, then you can utilize the built-in capabilities of your grapher, so long as it's on the calculator aloud portion. If it were on the non-calculator portion, we wouldn't give you a quadratic equation in your system along with a linear. We'd give you two linear, in which case you'd go ahead and graph the two lines on the same xy coordinate plane and look for their point of intersection, just like we did it in class and on your review. Does that make sense? Awesome. One to go. In order to solve a 3x3 system, we'd also be allowed the use of graphing calculator technology. First, however, we must go ahead and translate that original linear system into a matrix equation. How do we do that? Easy cheesy. We go ahead and grab my coefficients from each of my variables in turn, x, y, and z, and translate that into a coefficient matrix. Like last class, I'll do that in blue. The coefficient matrix is named because I just grabbed my coefficients from each of the variables, right, and focus in on this left side of the equal sign. So here we go. 1x plus 4y minus 6z means that my first row would be 1, 4, negative 6, and you guys know the rest. So I'll do negative 1, 2, negative 4. Go ahead and tell the class my last row when I call on you. What would that last row be? Caitlin?
2.
Awesome. Next, we'll have my variable matrix. My variable matrix, in order, is a point matrix from top to bottom. It's not x, y, the way that it was when we did our polygons in two-dimension coordinate plane. It's x, y, z, because we're going to find a solution point that's an ordered triple, x comma y comma z. And then equals, we still have an equation, it's just a matrix equation, and now my constant matrix. My constant matrix is the right-hand side of the equal sign, and again, that is a 3x1 matrix, top to bottom. Make sure you're in proper order. So you guys are checking my signs. And now we're ready to go. Now that I've written my coefficient matrix A, my variable matrix X, and my constant matrix B, I'm going to enter those in my calculator, A and B. Also that I can do my variable matrix X is given by A inverse times B on the home screen. Let's go ahead and do that. So in my matrix editor, I'm going to go ahead and enter a new matrix. I'm going to edit matrix A, and I want that to be, I'm going to want that to be 3x3. But my coefficients are 1, 4, negative 6. You guys check and make sure I don't mess up because I want to try and hurry. Negative 1, 2, negative 4, 2, negative 1, 2. Everybody good? Did I do that right? Everybody good? Catch me if I make a mistake. I'm going to edit matrix B. Matrix B I want to edit. And I want that to be a 3x1. And it's going to be negative 1, 5, negative 7. And now the big finish, we get to go to our home screen and we get to do A inverse times B. If I do A inverse times B, that would have gotten rid of, right, on the left-hand side, A inverse times A would get rid of the coefficient matrix and isolate that green variable matrix, get it by itself. Just like when we try to solve a regular equation, we try to get the variable by itself. By multiplying both sides on the left by A inverse, the inverse matrix of A, then we get the variable matrix by itself so we can see what it equals. Ready? Here we go. Home screen. I want that matrix named A. I'm going to take its inverse. Bam! Now I'm going to multiply it by matrix B. So I get the matrix named B. Boom! And then I'll go ahead and press enter. Voila! The calculator looks like it spits out my solution point, and I got exact values. Did you guys not get exact values? I must have changed it. It must have come from decimals that we could change into math frac, and so it looks like we don't even need that last question. Could you state the exact values of x, y, and z? Yes, it looks like x is negative 3, y is negative 1, and z is negative 1, and so that works out quite nicely. My solution then is, I'll make this a little bit bigger, negative 3, negative 1, negative 1. A quick check in the original. Negative 3 minus 4 is negative 7, plus 6 is negative 1. Opposite of negative 3 is 3 minus 2 is 1, plus 4 is 5. And 2 times negative 3 is negative 6, plus a positive 1 is negative 5, minus 2 is negative 7. So it satisfies all three equations. And again, on your quiz, you want to make sure you're checking right your answers because you can tell whether or not the solution points you found are indeed solutions to the original system by checking each one before you turn it in. I'm going to delete this because we don't need it. What questions do you guys have on your Bellwork today? Awesome. Then we're going to go ahead and pause the recording so we can take care of our homework check today. Okay, ladies and gentlemen, so today's content objectives, including solving and graphing linear inequalities in one variable. Before your quiz, right, we're going to have a short discussion, and the good news is that you already have solved and graphed linear inequalities in one variable, so we're going to remind you what that looks like during the first part, and then the second half of today's class will be taking your quiz. We'll recognize properties of systems and equations, and we're going to estimate solutions to systems by graphing, and we're going to continue working with linear inequalities the next couple of days. But first, let's go ahead and remind ourselves how we solve a linear inequality. Notice how it's just like an equation, except my relational symbol is not an equal sign, it's a greater than, or a less than, or a greater than or equal to, right? Those are my relational symbols for inequality. In order to solve an inequality, it's the same exact process as solving equations, with one exception. If you multiply or divide both sides by a negative number in the course of solving your linear inequality, you must reverse the direction of your inequality symbol. So once again, that only happens if you multiply or divide by a negative in the course of your solving. And the reason for that is that our solutions represent a whole range of numbers, either to the right or to the left of a particular boundary value. And so when we divide or multiply by a negative, we have to change the direction in which we look. Think of a negative sign as an opposite, right? So we want to look in the opposite direction. Anytime we multiply or divide by a negative, we need to split the direction of the inequality symbol, because now we look in the opposite direction to find our solutions to satisfy the original. Let's go ahead and do it. So guess what? Same inverse operation. I'm going to subtract 45 from both sides as my best first step. That will yield 6x on the left. Did I multiply or divide by a negative? No, I just did addition or subtraction, so I keep the symbol. On the right, negative 63 minus 45 is negative 108. Is that right? Negative 108. Good. Now to solve for x, I divide both sides by 6. That gets x alone. Hooray! Negative 108 divided by 6. I'll have to do that. And I get 120, 20, let's do 18. You guys give me 18? Negative 18? Awesome. And then I'll go ahead and say, do I need to change my direction? I divided. Well, I divided, but I divided by positive 6. I don't care that this was negative 108. I care that my division was by a positive number, so I do not need to change the direction of the symbol. This remains a greater than the entire time. So once again, we only reverse the direction of my inequality symbol if we multiply or divide both sides by a negative number. And here, we just divided both sides by a positive number, positive 6, so we don't change the sign. In order to graph this, we simply need two things. We need to show the viewer, do we include that boundary number, negative 18, in part of my solution, and which direction do we look to find my range of solutions. If x is greater than negative 18, right, I'm going to be looking everywhere to the right of negative 18, up the number line. My inequality symbol points the direction to the solution. So I'll go ahead and circle my boundary number, and I'll show you everywhere to the right, and I'll label my boundary number, and then I'll fill in my circle or not. If it's a strictly greater than, then it does not include my boundary number as part of the solutions. I'll leave this as an open circle, so I won't fill it in. Negative 18 is not included as part of the solution set. Negative 19 would not be included. Negative 17 would be included. Negative 17.9999 repeating would be included, and so on and so forth. So everywhere to the right of negative 18. All right, let's go ahead and do another. In this next one, I need to get rid of the parentheses, so I can go ahead and distribute through if I wanted to, or I could subtract that 2. Either way would be appropriate. And so you can solve this either way you want. I'm going to go ahead and subtract 2 from both sides. When I do that, I get negative 5 times quantity x minus 4. And again, I just add or subtracted, so I don't change the direction. Now I'm going to go ahead and undo this multiplication. That quantity that I want, x minus 4, is inside the parentheses. So I need to undo that multiplication and peel out the outside stuff so I can get in there and solve for x. When I do that, I'm going to divide both sides by negative 5. When I divide both sides by a negative number, or multiply both sides by a negative number, I need to flip the direction of the equality symbol. Dividing by the opposite means I need to look in the opposite direction to find my solution set. And so I'm going to change the direction, and I'll show that with a patent pending shooty-doo arrow. This less than or equal to is now going to be a greater than or equal to. So anytime we multiply or divide both sides of an inequality by a negative number, we have to switch the direction of my inequality symbol. Everything else is the same. So I still get x minus 4. Negative 20 divided by negative 5 is positive 4. And we'll finish it out by addition. It looks like go gadget arm. X is greater than or equal to 8. So we'll go ahead and we'll get my boundary number. In this case, 8. Label it. We'll shade everywhere to the right of, and this time we include 8 in my solution set. Why? Because it was an or equal to. So this is a closed circle. We include it in my solution set, and we'll shade everywhere to the right. Let's go ahead and label these circles. This was an open circle. Uh-oh. This is an open circle. It comes from a strictly inequality. We do not include that as part of the solution set. This is a closed circle. And we do include 8 as part of the solution set. Excuse me. Awesome. Everybody pick out a solution to that first inequality, the blue graph, and tell me your solution when I call your name. All right, what's the solution to this first inequality? Get ready. Jarrett. 4. Give me a different one. Ian. 0. What about negative 18? No. Everybody get a solution to this red graph inequality. So what's the solution to this right side inequality? Samantha.
8.
8 is a solution because it was or equal to, so it was included. Give me a different one. Rachel. 10, absolutely. 1,000, right? Everywhere to the right of an infinite number of solutions. All right, for compound sentences, we'll go ahead and include a range of values now that connect 2 or more inequality statements together. And so we've got 2 ways to join for our compound sentences. We've got and we've got ors. If we are talking about an and type compound inequality, we're looking at the intersection of the original inequality statement. And so typically the intersection then is the overlapping areas. Or is referred to as a union of sets. And so if we're finding the solution to an or type compound inequality, we typically can look to the right of one number to find solutions, or to the left of another number. And so those are like the opposite direction inequality symbols that you'll see in the graphs, versus the in between one number and another graph, right? Those are my intersection solution sets. Lastly, an intersection symbol is this shape that looks like an upside down parabola. It's not a parabola, it's not a U, it's an intersection symbol. And this one over here is not a parabola, it's not a U, it's a union symbol. Okay, that's synonymous with a or a union, versus the intersection symbol is an and type compound inequality. Typically, these graphs end up being between one value and another to get your solutions, versus a union typically ends up being to the left of one number or to the right of it. These may or may not be shaded in, depending on what the situation is. Let's go ahead and write a compound inequality that represents a given description. Suppose people 18 and under or 65 and older are eligible for discount fares on the city buses. Write a compound inequality for A, the ages of people eligible for discount fees. Then we'll graph the compound inequality. So in this case, people are 18 and under or 65 and older. So I start off with my ages A that are 18 and under, so that would be less than or equal to 18, or A could be greater than or equal to 65. Now in my inequality, I'll simply put my boundary numbers, 18, 65. I'll circle my boundary numbers, and I'll shade. If it's or equal to, I include it with a closed circle. If it's strictly, I leave it open. Sometimes one is closed and one's open. Then for A greater than 65, I shade to the right. For A less than 18, I shade to the left. And I can pick out solution points from either the left region or from the right region. So everybody find your solution A that satisfies the original inequality. What's one solution A? Joe? 7 is a solution, right? 7 is a solution. Give me a different solution value for A. Will? 75. Notice how we can grab solutions from the left or from the right in an or type compound inequality. Nice job. Suppose people older than 21 and younger than 60 can drive those city buses. So now we've got an and type compound inequality. An and type compound inequality could be rewritten with an and in it. So we could go ahead and say that my age is D for drivers. D is older than 21, so greater than 21, and D is less than 60. We could write this as a string, where we start with the least most value of my solution set range would be 21, is less than or equal to all my values D, which are solutions, which is less than 60. Either way is appropriate to write this. If I write it the second way in blue, it's easy to see what my graph looks like. My solution set D lies in between 21 and 60. So I'll get my boundary values, 21 and 60. It was strictly, so I won't fill them in. These are open circles, and where will I shade? I'll shade in between them, because my drivers could be in between 21 and 60. Those are my drivers' ages. Are we good? Yeah. All right, let's close it up so we can do our quiz. What's the only procedural difference when solving inequalities versus solving equations? The only thing I do procedurally differently when I solve algebraically. And second, when graphing single variable inequalities, how do you know when to make an open versus closed circle? Go ahead and be ready to share your responses. I'm just going to give you guys about a minute to get those ready. Okay, so when solving an inequality versus solving an equation, what's my only procedural difference when I do that algebraically? Aaron?
You have to flip the sign when you divide by a negative number.
Good. When you multiply or divide by a negative number, we must change the direction of the inequality. Good job. So when we multiply or divide by a negative number, so that's when we multiply or divide both sides by a negative number, then we must switch the direction of the inequality. Of the inequality symbol. When we're graphing an inequality, how do you know when you should make an open versus a closed circle? So how do we tell whether we should do an open versus a closed circle? Jacques?
You'll know because if it doesn't have like the equal to, it's open, and if it does, it's closed.
Good. So the strictly greater than or less than would result in an open circle where you don't fill it in, it's not part of the solution set, versus closed, right? Closed, Emily?
That's when it has the little equal sign of it.
Good. That's the or equal to, right? The or equal to. And that would be the greater than or equal to or the less than or equal to. And it is included as part of the solution set. You guys are awesome. When you're finished with your quiz, you can begin working on assignment number 5, and I'm going to stop and save the recording to our Moodle.